Hi everyone, thanks for coming. Small disclaimer before I start. So couple of days ago I got sick, got some cold, so please bear with my voice for this half an hour, and let's start. So my name is Andrey, and today I'm going to tell you in the engineering story of how a not yet widely known search engine written in C++ won the benchmark. And this story is specifically about how we did this, so what we've done to make this happen. But before I start, before I move forward, let me introduce myself first. I spent pretty much my entire career at the intersection of search and databases. And back in 2016, I started building a C++ search engine as a pet project. And a couple of years later, it grew into ArangoSearch. It's a search engine natively integrated into ArangoDB core. And eventually we made it into top 10 search engines on DB Engines ranking. Today, I'm co-founder and CTO of SereneDB. It's a Berlin-based startup where we are building a search and analytical database where our search engine, IResearch, it stands for Information Retrieval Search, plays the key role. And let's start by looking back at how a search engine market was actually formed. And here I mean search libraries specifically. And actually it's a fairly narrow market. So the first ones were Lucene and Xapien back in the early 2000s. Xapien has never really caught on, unlike Lucene. And for the next decade, people have been trying to port Lucene to other languages. And we got Lucene, Lucene++, C Lucene, we got Lucene.NET. But these ports were mostly blind ports of Java code to these specific languages, and none of these projects has ever been really successful. Fun fact though, for example, RavenDB moved off Lucene.NET only in 2023, and Single Store moved off C Lucene onto Vanilla Lucene only in 2024. So Lucene had became the de facto standard for the industry, but people still wanted an alternative in their own programming languages, so it's easier to embed. Around 2015, so-called the second wave of search engines arrived. And the difference was that developers rethought how Lucene architecture could best fit their specific language. And we got Belief in Go by Couchbase, we got Tantivy in Rust by Paul Mazurel, and we created IResearch back then. And let's see how it formed the market. So, as we know, Lucene is pretty much everywhere. So search servers like Elasticsearch, OpenSearch, Solr are powered by Lucene. Lucene is inside managed offerings, inside Azure AI Search, inside MongoDB Atlas. Lucene is in databases, so Neo4j, CreateDB, again, Single Store use Lucene, and pretty much every single Java database you can name more likely use Lucene under the hood as well. From the second wave, Tantivy is the most popular engine, and it powers QuickWit, now a part of the Datadog, and ParadeDB. And apart from it, it's also used in really a lot of Rust projects. And it became popular because not only because of its authors, but also because Rust ecosystem itself is growing really fast. But how do you actually compare search engines head-to-head? So in SQL world, we have pretty much the whole set of benchmarks we can use. We have TPCH, we have TPCDC, TPCDS, sorry. We have ClickBench. But in search world, there was nothing like that. And then Tantivy team built Search Benchmark the game, and that was a really important step for the search community. Because suddenly, out of nowhere, you had a standard set up to try your ideas on and try to improve them. And any benchmark is actually not about being selfish. It's not only about the competition, it's about moving the whole industry, the whole field forward. It's very important for the particular area. Let me show what it actually measures and the rules of these benchmarks. So we have document corpus as a subset of English Wikipedia. It's fairly small, so only 5 gigabytes. So small enough to fit RAM. The queries are derived from American Online query dataset. They're kind of real queries with no personal information, mostly multi-term. The execution is single-threaded on purpose, and any search engine level caching is disabled. The benchmark driver talks to every engine over standard input and standard output, one query by one, and it measures wall clock latency. And before timing actually starts, there is a 60-second warm-up phase, and this is actually quite important for the benchmarks because this warm-up phase ensures that the index stays in operating system page cache. And for Java machine, it also allows it to cache some hot paths. So on the right, you can see query types it checks. So there are high-frequency term, intersection, union, phrase, required, optional, negation, and two-phase, which is a composition of term and the phrase. And there are 3 collection modes. So count, which counts only all hits without performing any scoring. Top 100, which returns 100 best results and allow engines use so-called pruning algorithms because they do not need to return the total count. And top 100 plus count, which forces the full scoring for every match, and this is basically the pure scoring throughput test. And back in March, we added IResearch to the competition and ran tests against Vanilla, Lucene, and Tantivy. And this chart is an excerpt from top 100 plus count mode with 4 query types. And what is the most noticeable here? First of all, IResearch is faster on every query type. And the biggest win is in union, where we are 3.6 times faster than Lucene and 2.4 times faster than Tantivy. But even on the smaller lead, on the intersection, we are still 1.5 times faster. There is no clear second place. So on union and phrase, Tantivy leads, while required optional intersection, Lucene is faster. And you can check these benchmarks. It's publicly available on GitHub in QuickWit repository. So this commit was accepted by Tantivy contributors. But why am I showing this? Because this mode, top 100 plus count, is the most computationally intensive mode with respect to scoring, and the whole rest of the talk will be about block scoring. And I really think it's the next real frontier for the information retrieval engines, and I'm really proud that we adopted it early on. But before diving to this optimization, let me remind you how a typical search query look like from the perspective of the engine. So every search, no matter how it looks, built from the same building blocks. So incoming query, one way or another, is split into terms. Then for each term, we look up so-called postings list, and posting list, as you all know, is just a set of documents containing a particular term. Once engine has this postings list, it passes it to the query, and then the query should combine it in some way to get actual matches. So for end query, we have to intersect this list. For OR query, we have to union those lists. And then for every match, we have to assign a score for every document. And the score is typically a floating point number defining how relevant a particular result, a particular match to the search condition. Once everything is scored, we can sort them by score, keep the K, and here is our result. And so we are currently scaling down to this purple box. Few notes about scoring. So scoring itself is what makes search engine search engine, because it's a major task for search engine to score documents efficiently. And logically, it can be quite trivial, right? So we select a set of documents. performing some calculations and evaluate this expression. So it's like just like executing a function. But in practice, it might be quite heavy. Real scoring might combine dozens of signals to produce the overall score. Some of such signals are stored inside documents, so-called authority signals, and such as PageRank, recency, or click-through rate. Some of such signals are evaluated or computed on the fly. And the well-known BM25 is exactly one of such frequency-based signals. It's built from frequency and document length. And as I said, for every document should be computed. So now what I would like to say that traditionally, Lucene and Tantivi use so-called documented time approach. They compute BM25 for a document. To compute BM25 for a document, they first read frequency and norm from the storage, evaluate the formula one by one. It's quite simple, right? But the problem is the performance. And in practice, I've seen profiles where up to 50% of the query execution time was taken by just evaluating the score. And to make this a bit better, to make documented time approach a bit faster, Lucene and Tantivi do a couple of tricks. So the first trick is quantized norms. So what they do, what norm is basically the length of a field in a document or a document itself, depending on what you index. And it's typically represented as a 32-bit integer. And if we would compress this 32-bit integer down to 8 bits, of course with some precision loss, we then can build 256 entry lookup table and substitute some computations with potentially cheaper table lookups. And why it might be bad? Because of course you lose some precision when compressing these norms, and you also need to write custom code for every scoring model, which is kind of tedious. The second trick they do is so-called scoring devirtualization. And if you know that Lucene has an extensible similarity framework, which is actually a driver of its popularity as well, because it allows researchers to plug in their own ideas and test them. But during the execution, scoring is called multiple, several millions of times actually. And there is no way for, since this call, the scoring call is opaque for a compiler, it's impossible to optimize it. A compiler cannot optimize it really well. So to make it a bit better, Lucene relies on devirtualization of Java machine, basically on the native optimization. But Tantivi, they made an opposite and radical choice. So they ship one fixed BM25 score with constant, with pre-configured K1 and B coefficients. So if you want to change it, you have to recompile it. And for us, it felt like fighting the consequence, not the root cause. And we wanted to have something universal to improve this scoring. And if you look at how SQL engines do this, they actually solved this a long time ago. So with block at time approach. And the idea is quite simple. So we take a block of data. Inside the block, we have input registers that should be already filled, and some out registers which have to be filled after we're performing the computations on the block. Why is it good? Because the cost of calling such a function is negligible compared to the amount of work it does. It's good because we can vectorize computations using SIMD and AVX instructions available on every modern CPU. And as a result, we don't need all these tricks. So we can just write our function. It's quite simple, it's quite straightforward, and literally we can get this after vectorization for free because most of modern compilers do this. And actually, it doesn't matter what to compute. Our formula can be very complicated. So again, we have to just fill the right registers with the right data. But if it were so easy, why it's not yet done? Well, because in terms of search engine, it's very easy to do it in the wrong way. So the block approach, first of all, needs data laid out in a seamed-friendly manner, and the risk of overfetching is really high. And since search queries often, especially in these benchmarks, they are sub-millisecond latency, this kind of work might involve significant overhead. So initially we thought, okay, let's represent scorers as functions and let's preallocate these blocks of memory. Then the iterator will fill some cells in these blocks with doc IDs, with frequencies. But how big should a block be? If you look at analytical engines, for instance, DuckDB, they use blocks of size 2048 elements. But for us, it's clearly too much, because inside the engine, postings lists are already split into blocks of 128 documents, and 128 for us is clear upper limit. And as we require AVX2 instructions and have 256-bit registers in place, we can process 8 values at time, so 32 should be a good default, right? So our plan is simple. Then we have to accumulate the block, we have to score it, and repeat. So since we have chosen the block size, we are ready for our first try, and let's see how end query works. So for every match, end iterator, as I mentioned, it records doc ID into the corresponding cell, and it signals other iterators, so term iterators, to put their frequencies to other corresponding columns. When the block is filled, when the block is of 32 documents is full, tuples, sorry, is full, we read norms from the columnar storage into the corresponding column, and then we are ready to perform the computation. And note that unlike Lucene and Tantivi, in this particular case, we read norms from columnar storage only once per document. And it works perfectly. So conjunctions became really faster, we were happy, and then we tried it on disjunctions, and we failed, we miserably failed. Then we started looking at what's happened actually. And it turned out that for high cardinality queries, copying data from one place to another actually made things really worse. It's not only because we do extra work, but also because we touch different memory locations, meaning that we evict data from CPU cache. And we started thinking of how we could do better. And we realized that we potentially need completely different execution strategy for such greedy disjunctions. And think about how conjunctions are different from disjunctions. So conjunctions try to skip across the postings list, so they pull sub-iterators. While disjunctions, they have no other choice other than scoring everything. They will score everything anyway, so why to postpone scoring? Let's push down scoring closer to the place we read the data. So we thought, how would it work? And we realized that it's really nice approach, because luckily enough, in the format, we have a document block stored next to frequency block. So we already have 2/3 of the BM25 formula in place. So the only thing we need is to, again, read data from the columnar storage, and then we are ready to perform the computation. But notice how this is fundamentally different from the conjunction approach. So here, the blocks are 128 tuples, and we may actually read norm for the same document multiple times, but we do not copy any values. So we basically perform computations on exactly in the place where they were just touched, where they were read. So in the end, the only thing Union has to do is to combine these scores because they are already pre-calculated. And it of course depends on the query. So for Levenstein, you probably need to take max value. For others, just sum them up. So yeah, it really depends on the query. And have we eventually won? Well, yes, you saw this on the slides already, but that was top 100 plus count. What about top K? And for top K, it's a different story, because so far we discussed only two strategies. It's late scoring for conjunctions, when we pull up the scoring computation, and greedy scored for disjunctions when we push down this computation. But for top K retrieval, it's a bit different. So if we would score every single match, it would be a wasted work. So, and in order to win, we have to skip what can't win, actually. And that's our third strategy. So modern information retrieval, there is a set of so-called pruning algorithms. And these algorithms is what makes top K queries work really fast when you have billions of documents. And one of them is block max score. And the idea of the algorithm is to split the term into groups, so essential and non-essential groups. And essential terms are the terms which have to be scored for a document to make into the top K. While non-essential terms, they are usually low IDF, quite very common words. So basically just an add-on to the essential terms. So basically you can skip documents that do not hit any essential term. But I won't go into details here because this topic deserves talk on its own. The only thing I'd like to highlight is in block scoring paradigm, the essential part behaves like a union, so with greedy scoring or scoring with scoring pushed down, while non-essential part is more like an intersection. So it's kind of hybrid strategy. And block scoring is a big and interesting topic for sure, but on its own, it wasn't enough to win the benchmarks. Honestly, I do not have time today to cover all the optimizations we measured. So if this is interesting to you, we have prepared a series of deep dive posts about it. Just follow our blog and look for search optimization journey, or just scan a QR code. We would love to see you there. And the honest thoughts about these benchmarks. So it was designed to test inverted index performance, and it does the job. It does it really well. But in the context of real search and analytical systems, it looks more like MICA benchmark. So real end-to-end benchmarks should include the rest of the system as well. So indexing speed, storage layer quality. It should check how efficiently do you handle deletes and updates. And of course, in 2026, the dataset should be a lot bigger. So, and at SereneDB, we are currently working exactly on that kind of benchmarks, and we plan to release it quite soon in July. We actually want search world to have something like ClickBench, basically the standard way to compare engines, because as I mentioned before, that's what moves the whole field forward. And we actually need your help. We want this benchmark to be as open as possible and as honest as possible. And we invite you to participate. So please add your favorite products, tune them the best way you can, add more test cases. So let's build these benchmarks together and see how can we move forward together. Thank you for your attention. So the code is on GitHub. Every star matters for us. If you would like to discuss other topics, with my colleague Alexander, we're here over the lunch. So thank you.
Thank you, Andrey. Are there any questions to the talk?
Do you think that GPUs creates new opportunities to design a search engine now?
It's hard to say, because like with this approach, I think again we will be just overfetching data because the block size is really small and it's already quite fast. So these benchmarks is mostly microsecond latency, right? So even copying over data to GPU, right? So it will eat everything. If we would just move the whole thing onto GPU, probably, but then it's completely different thing, right? So probably makes no sense for us because it's already quite fast.
Thank you.
Hi, nice talk. Thank you. I'm wondering about the feature set compared to Lucene. I mean, is there something you cannot do compared to Lucene and so on?
No, it's full.
It's full. Okay.
It's full.
Yeah.
Yeah.
Thanks.
If you like, I can explain like over the lunch, like what full means, but it actually covers everything, pretty much everything.
Well, full means all.
Yeah, exactly.
Anyone?
Hi, thanks, very informative.
Thank you.
Wanted to ask how how do these optimization work in case something changes? Like, do you assume that the blocks that you're looking at remain for a while?
Yeah, here we have a kind of snapshot isolation. So we have these segments and we fix certain snapshot like at query time, and it's immutable at query time. So there is no possible something will be changed inside the query.
Got it. Thanks.
Anyone else? Okay, I will not hold you any longer because we have lunch. So we probably want to get fast in the queue. We'll be back at 2 p.m. for the next talk here. Thank you very much.
Thank you.
Thank you.